Hey Lisa, just want to say that I really love you. You're a wonderful person. The best girlfriend I could ever wish for. Woo. Good morning, fellow mathematicians. Welcome back to another video. Once again, it's time for
Papa Flammy's Random Week.
Oh yeah, let's go ahead and get started. So, we've got some bad news and some good news. So the good news at first. Today's my birthday. Hey, I turned 24. I'm an old boy now. I'm very old already. And the bad news is that's the last episode of Papa Flammy's Random Week. I'm terribly sorry for that. And we are going to end it off with some Putnam boy right here. Let's take a look at that. So what's the problem that we are going to solve today? So let's suppose we have some I with respect to x, and it's constructed like this right here, where I of x is a polynomial. That also means that all those things right here, those a of t, c of t, are also polynomials. And what we want to show is that x minus 1 to the 4th power does indeed divide I with respect to x. So that's what we want to show today. And I have rewritten this a little bit, this weird horrible expression into a of x plus times b of x minus c of x d of x. So we are rewriting this like this. Okay, and at first I want to take a little detour into abstract algebra, you could say, into some basics of algebra, because we can't really tackle this problem right here without the proper groundwork. Oh, English is hard. No, it's not. I'm just saying this for fun all the time. So let's go ahead and get started, and let's take a little look into algebra. Just like I said, we want to lay some groundwork. We want to go a little bit into the theory of algebra, just a little bit, polynomials and stuff like this. So at first I would like to get out of the way what it means for something to divide another something. For example, does the number 2 divide the number 6? Yes, it does. But why? So 2 does divide 6. We are denoting it like that, but we can rewrite it as follows. That's equivalent to saying 6 over 2 is equal to, well, this is going to be 3. And that's what it means for something to divide another something. We want to end up with an integer solution on this side, right here, without a remainder. We can rewrite this because 2 isn't equal to 0, so multiply it on both sides. That 6 is equal to 2 times 3. And indeed, 2 does divide the number 6. Is there a counterexample where something doesn't divide another something? Well, instead of 6, let's take a look at 7, for example. So 2 does divide 7. Let's claim that this holds. That means we are going to rewrite it as 7 over 2. Well, this is 3.5. That's not an integer solution. That's not good. But we can rewrite this a little bit different as 3 with a remainder. I'm putting it like that because in Germany we are going to write with a rest of something with a remainder of 1. And if we have a remainder, something does not divide another something, so 2 doesn't divide 7. And we can rewrite this equivalently as 7 being equal to 2 times 3 plus 1, with 1 being the remainder in this case. So we have derived this for simple numbers. Can we expand this idea to polynomials, this concept? Yes, we can. So at first I would like to take a look at this second example right here, just with polynomials. Let's assume that some polynomial h of x does not divide f of x. So h of x does not divide f of x. Putting it into this form right here, we can rewrite f of x as h of x. I just wanted to write a blank constant because, I don't know, muscle memory. H of x times g of x plus some remainder polynomial r with respect to x. So that's what it means for a polynomial to not divide another polynomial. What happens if this remainder is exactly 0? Well, that means that a function, this polynomial, does indeed divide f of x. So let's assume that h of x does indeed divide f of x. That's equivalent to saying that f of x is nothing but some h of x times g of x with a remainder of 0. Okay, nice. But how does this help with this problem right here? So if we take a closer look at this problem, we wanted to show that x to the 4th power minus 1 does divide I with respect to x. maybe we should take a look at a thing called roots of a polynomial. So what does it mean for something to be a root of a polynomial? So R is a root of f of x. Let's assume this. So R is root of f of x. I forgot the off here. Doesn't matter. That means if we plug this very R into x right here, so f of R, we are going to end up with a 0. But if we take a look at this definition, we can rewrite this statement a little bit more into R minus R times G with respect to R. So I hope you can see where this came from. R minus R is going to be 0. That means this whole thing is going to be 0, since G is just a polynomial and it's multiplicative. Okay, but what does it also mean for R to be a root of f of x? Well, it means exactly that x minus R does divide f with respect to x. We can use this definition right here on this to say that f of x can be constructed as x minus R times g with respect to x. And I hope you can see where this came from, because if we plug in r into here now, that's r minus r times g of r. That's exactly this definition for a root right here. Is there a little example to show that this is indeed true? Well, let's take a look at a famous one, I would say. So f of x being equal to x squared minus 1. We can factor this a bit into x plus 1 times x minus 1. If you say that g of x is now this thing right here, that also means that x minus 1 is going to divide f of x in this case. And also, if you assume that g of x is this thing right here, that means that x plus 1 is going to divide f of x. So this thing right here has exactly two roots. Those roots being minus 1 and 1 in this case. That's just using this definition right here of the root on this right here. And you can immediately see where this comes from. But what would happen if we would differentiate this very polynomial here? So let's put it here. So what's f prime with respect to x? We are going to end up with just 2x. What happens now if we plug our roots into here? Are they still roots of this polynomial? So if we plug in minus 1 into here, we are going to end up with minus 2. That's not equal to 0, so minus 1 isn't a root. And if we plug in 1 into here, that's just 2. That's also not a root. That's not equal to 0. So that means by differentiating, we have removed one of the roots from this polynomial down here. But is there a way for us to preserve roots? We are going to take a look at this now. So I would like to talk about repeated roots now. At first, let's take a look at our f of x once again. So let's suppose that r is root of f of x. Well, what does it mean equivalently? F of x is nothing but x minus r times some other polynomial g with respect to x. And what it also means is that x minus r does divide f of x. Keep this little fact in mind. And you saw before that we are removing roots when differentiating a polynomial. But we now want to suppose that r is a repeated root. You will see in a second what I mean. So why not differentiate f with respect to x and see what we get at first. So f prime of x. We have to use the product rule on this right here. So at first we are going to end up with g prime of x times x minus r, and then plus just g of x in that case, because this differentiated is just 1. So plus g of x. And now we are going to suppose that r is a repeated root. That means that r is also a root of this polynomial. So let r be a root of f prime of x. What does it mean for r to be a root of f prime? Well, that also means that f prime of r is supposed to be 0. We can plug this r into all the x's right here. So this is g prime of r times r minus r. That's just going to evaluate to 0 plus some g with respect to r. And when I first saw this in abstract algebra, I just thought, boy, that's really cool, to be honest, because if you take a closer look, f prime of r is 0 is exactly g with respect to r. That means we have plugged r into this polynomial g with respect to x and we ended up with 0. But what does it mean if we plug a value into a polynomial and we end up with 0? That's the root of the polynomial. So that also implies that r is a root of g of x. We can rewrite this as g of x being equal to x minus r times some, I don't know, h of x. And that also means that x minus r does divide g with respect to x. And now we have a proper definition for our g of x that we can plug into our original equation right here. So that also means that f of x is now, well, this is going to be squared. So x minus r squared times h of x. Just plugging this information in. And what we are going to notice now is if we plug in r into here once again, we are going to end up with 0 once again. So that's still a root, it's a repeated root at that. And the thing is, now by this definition, x minus r squared does divide f of x. So you see, there's a connection between repeated roots, differentiation, and powers of this root term right here. Is there a connection between this thing right here and our original problem? No, there's not. I just did it for fun. Yes, certainly there is. So you see, we have x minus 1 to the 4th power divides I with respect to x. So what that also means, if we could just show that here in this case 1 would be our root, that 1 is a root after differentiating the first time, then the second time, then the third time, we have indeed shown that x minus 1 to the 4th power does divide I with respect to x. And well, that's our goal for now. And just like I said, this problem is quite straightforward, but it's hard if you don't know any of those facts down here. So let's differentiate this thing a first time and see what we get. No! At first we have to see if 1 is even a root of this first polynomial. So what if we plug in 1 into all the x as well? We have an integral from 1 to 1, then 1 to 1, 1 to 1, 1 to 1. An integral from a to a is always 0. So that's 0 minus 0. This is 0. So I of 1 is indeed 0. So let's conclude that. I of 1 is 0 is equivalent to saying that x minus 1 does divide I with respect to x. And just like I said before, we just need to differentiate it 3 more times to get to the 4th power in this case. And if 1 is a repeated root to this point, we can safely assume that x minus 1 to the 4th power does indeed divide I with respect to x. So let's do this. So this right here is really straightforward, and at a certain point I'm going to speed the process up and you can watch the bonus videos if you want to see all the differentiation, because it gets quite messy. So at first I would like you guys to remember how to differentiate an integral like this. If you take a look into the description, there will be a link to the Leibniz rule for integrals. If we differentiate, for example, a with respect to x, we have to use the partial derivative with respect to x in this case, of all the terms inside. This is going to evaluate to 0. Also, the lower bound just gives us 0 in that case, because 1 differentiated with respect to x is just 0. So this term vanishes. And also, we are going to evaluate those two functions right here at the point x, so as a constant at the point x, and differentiated x with respect to x, which is just 1. What that means exactly, a prime of x, for example, is just going to evaluate to a of x times c of x in that case, yeah. So that's what it's going to evaluate to. You can take a piece of paper, try it out for yourself. It's just how it is. And as you might notice, at first I'm not going to write this of x all the time. There would just be too much writing. But we have to use the product rule right here 2 times at the first iteration. So what is I prime with respect to x? Well, at first we are going to end up with a times c times capital B in this case. Okay, now we have to differentiate the b part. So we have this capital A left, and b differentiated is just b times d, all with respect to x. And then negative. Don't forget the negative signs. c of x differentiated is just this thing right here. So a times d times capital T. That's the dead if you turn it around. So let's make a dead out of that. I'm the papa. And the last one, negative. So c stays as it is, capital C, b times small c. Okay. Now we want to find out if 1 is indeed a repeated root. So what is I prime of 1? Well, we are going to end up, if we plug a 1 into all those capital things, it's always going to evaluate to 0, just like with the first iteration we've done, I of 1. So that means that 0 plus 0 minus 0 minus 0 is indeed 0. So what we can conclude, x minus 1 does divide I prime of x, which also means that x minus 1 squared divides I of x. So we have done the first iteration and now we are off to the second one. So how are we going to get the second derivative? Well, we just have to differentiate the first derivative once again with respect to x. And now we have to use the product rule a lot of times. So I double prime with respect to x is now. Okay, so we have done this now, and let's see if anything cancels out. Well, if you take a closer look, this thing, this thing, this thing, and this thing is going to cancel out. They have inverted signs, so that's quite nice. And now you see, we are going to end up with a lot of terms, but all of them have those capital A's to D's inside. I'm giving you the D, my boys. So that means if we plug in a 1 into y double prime, that means we are going to end up with a 0 in the end. That also means that I double prime of 1 is 0, which means x minus 1 does indeed divide I double prime, but especially this means x minus 1 to the third power now does divide I of x. And now we are nearly done. Let's just do the last iteration and see if it holds for the last one. And we are off to the finals, my boys. Let the memes start. And now we are done, my boys. That took quite a while, probably 2 minutes or something. And now let's see if something cancels out. We just need to see if everything has an inverted term, you could say. So BD A prime C, that's positive and that's negative. So this and that is going to cancel out. AC B prime D, this and that is going to cancel out. Wonderful. BD AC prime. BD AC prime, and that is going to cancel out. Now let's take a look at ACBD prime. ACBD prime, this is going to cancel out. And now the most satisfying part, all that's really left are those terms involving those capital thingies of x, those capital polynomials you could say. That means if we plug a 1 into this triple prime, I triple prime with respect to 1, we are indeed going to end up with 0. That also means that x minus 1 is going to divide this triple prime boy. But that also means that finally x minus 1 to the fourth power does indeed divide I with respect to x. I'm placing a black boy here and then we are done, my boys. I failed miserably. That was supposed to land in here. Here you can see, it was supposed to land into here. That's it. I think the most satisfying thing about this exercise is the path you have to take in order for us to solve this right here. If you did enjoy this video, please like and subscribe and recommend me if you like. If you enjoyed this whole goddamn week, my boys, then please like and subscribe, recommend me if you like, and share those videos everywhere. I would highly appreciate it. If you want to support me a bit more, link to my Patreon will be in the description. Recording all this stuff, all those very long videos was quite a journey for me in the last few days. So I hope you very much enjoyed it. Please support me on Patreon. I would appreciate it. I still have to pay for the camera. It was really expensive. So please spend $1 on me or something. I hope I'm worth this much. Never mind. Even if you don't, I'm just glad that you are watching my videos. Up until the next video, have a flammable day. See ya. I love you guys.